Okay, so I believe I'm live. And all. I actually coded earlier today because I just don't code in the evenings. It doesn't work like that. I know that's like the strange habits of developers, but I was learning or relearning stacks for Python because I need to do some interesting things this year. So, what we're working on, however, today is if you've been tracking with me for the past 3 weeks or so, I am holding myself accountable to studying different deep learning topics again, or release again. And I'm welcoming anyone who wants to sit down and study during this time with me. But really, it's going through materials again, running notebooks, trying to code out stuff, and get an understanding of how it works again in my mind, in my mental space, because a lot of the markets that I work into are going either more into econometrics, statistical learning deeper, like experimentation, or they're going into deep learning a lot more than they were previously. And so I need to make sure that I am up to date on all the technologies and can still be hands-on when necessary for working with my more junior developers. So we've been going through this week, looking again at vector mathematics and the things that go into that. Yesterday and the day before, we were in section 1 and 2. I'm actually going to pause before going into section 3. And I wanted to spend some time reading through non-negative matrix factorization, because while I did learn SVD and SGD, I did not remember anything about non-negative matrix factorization. It was just not pulling up in my mindset. So what we're going to do is we're going to spend some time going back through this to understand the how and why behind it. I understand this, like frequency documents. I've done that since I started my career, just not in packages, right? But non-matrix factorization isn't stuck in my brain to where it's not even like coming up from a long lost memory. So I am going to click on a lot of resources in here and see if I can either jog a memory about non-matrix factorization or relearn it or learn it for the first time. If I can't jog a memory, I'm probably learning it for the first time. So we're going to look at that, and starting with they have a lot of stuff here. I'm actually going to see if there's an interesting video. Actually, let me do it this way. Keyboard. Clickety click click. Okay. Let's see who has videos. Stats Ninja. I wonder if Stats Quest or One Blue 3 Brown has a video. I like their videos. No, he doesn't have that. And let me check. 3 blue, 1 brown. He does have a video on matrices, but that's not what I'm looking at. That's the next section, LU decomposition. Okay, so we're going to just look at one of these people I don't know, and we're going to hope that they have some pretty good videos on this topic.
Hello and welcome, my name is Emmett and welcome to another tutorial. So what is NMF? NMF is non-negative matrix factorization. Imagine I have a matrix X with a dimension of n by m, which is a non-negative matrix. By non-negative matrix, I mean it doesn't have any negative entries. And we want to factorize this matrix into two non-negative matrices, W and H, in the way that W is n by k and H is k by m. So in order to do it, we need to solve a minimization problem. We need to minimize the distance between X and W times H with respect to W and H. And we have to keep in mind that W and H don't have any negative entries. But this problem is an NP-hard problem because it is convex in W or H, but not in both. If you ask why, here is the proof. Consider the scalar case where m and n equal to 1, then the problem is going to be like this. And then if you compute the first and second gradient of it, we are going to see that the Hessian or the second gradient is not positive semi-definite for all the values of x, w, and h greater or equal to 0. So this problem cannot be solved analytically, so it is generally approximated numerically. It means that for this minimization problem, we cannot find a global minimum. However, finding a good local minimum can be satisfying for us. Therefore, we are going to use an algorithm called multiplicative update introduced by Lee and Seung in 1999. This algorithm is based on gradient descent with different update rules. So basically in this algorithm, at first we randomly initialize W and H. And in each iteration, we fix the W and update H, and then we fix the H and update the W. Lee and Seung has proved that under these update rules, gradient descent ensures the convergence of this problem in limited number of iterations. We won't get deep into mathematics, but what they did is that they used additive update rules and they set the learning rates in this way. And finally, they get the multiplicative update rules. I implemented this algorithm in Python and I uploaded it on my GitHub. You can find the link in the description below. Thank you so much for watching this video. Don't forget to subscribe my channel. Be safe. Stay at home. See you next time.
Ever wondered how Facebook identifies faces in photos or how Google groups your images by people? Stay tuned to find out. Identifying people is an effortless task for humans. Our brains remember thousands of faces, recognize them within split seconds. However, it's not that easy for computers. It's because of the variations in face, expressions, and lightings in different photos of the same person. Our brains identify different people by recognizing different features, like the color of the eyes, the shape of the nose, or even mouth. However, for a machine, an image is just a...
It starts too much at the beginning.
Hello. For our CSC 466 Knowledge Discovery from Data final project, we decided to implement non-negative matrix factorization. I'm in a group with Andrew Kishishian, Griffin Johnson, and myself. I went ahead and implemented non-negative matrix factorization, otherwise known as NMF, and then Andrew and Griffin went ahead with the experimentation on it, as you'll see in their videos. So a little bit of background on what NMF is. It's an unsupervised machine learning technique created by Lee and Seung in 1999. So it's pretty modern. It's a versatile algorithm because it makes for a parts-based representation of its input data, which can be used for many things. The non-negativity of its input is what allows
A CRM shouldn't weigh your budget.
This versatility. So there are many uses because of this. One of them is the main one that we'll be talking about in this project. It's dimensionality reduction. And some other ones are data compression and approximation, audio source separation, and text topic extraction, to name a few. So here are the basics of the NMF algorithm. It is given a matrix V as its input of dimension f by t, and what it does is it learns V's approximate factors, W of dimension f by k and H of dimension k by t, where there's a constraint on k where it needs to be less than the minimum dimension, either f or t, for usability reasons. So all matrices must contain only negative values, as this is the effect of the input matrix being non-negative itself, and this is what allows that parts-based representation. And then the real cool thing about this is that W and H can then be multiplied together to make V prime, which is an approximation to our original matrix that we input, V. So that's fine and dandy, but how does this actually work? Why can these two matrices approximate V? Well, this is how it works. Well, first you have V, which is your original non-negative data. And what it is basically a sideways data set of what we're used to dealing with, where the columns are our samples, and then the rows are our features, T columns of F-dimensional data. So that's fed in. And then the two matrices that are made, W, one of them, is the basis vectors, are also known as the dictionary matrix. And what this is a set of things where a linear combination of any of these things approximates any sample in V. So they're kind of like building blocks, you could say, where each column is one of these things, and they're called the basis vectors, where H is kind of the complement to W, and it's called the activations. Each column in these activations matrix encodes a linear combination of all basis vectors that corresponds to a sample in V. So they're kind of like the instructions, you could say. An analogy would be maybe the basis vectors are like building blocks or Legos, and then the activations are like your instruction manual or like the instructions to build this Lego set. So these activations could also be called weights or gains because they tell how much of each basis vector should be used to actually approximate a sample in V. So let's talk about a big use case of NMF, and that's dimensionality reduction. Dimensionality reduction is the task of transforming a data set with many dimensions or features, those are two of the same, they mean the same thing, into a data set with fewer dimensions. So we want to do this while losing the least amount of information possible. And the reason for this is because it's a method that, there's going to be some information loss, as you can see. We already know a dimensionality reduction method, that's PCA. In PCA, you have these things called principal components, right? What principal components do is they are essentially these orthogonal axes in a data set space that describe the axes of greatest variance in the data. And as you can see on the left side of the figure there, that makes for essentially lowering the dimension of the data set if you use fewer axes than the axes in your original data set. For example, there's 3 here in our original data set, and then you can approximate that down to 2 with PCA. Well, NMF does essentially the same thing because of this thing called basis vectors. If you think of linear algebra, basis vectors are unit vectors that have the ability to, that let you make any possible vector in a vector space, as in any possible vector is a linear combination of the basis vectors. So as I just explained with NMF, you can have a number of basis vectors, and if this number of basis vectors is less than the original number of dimensions or features in your original data set, then essentially you already have dimensionality reduction going for you, because this H matrix that's paired with this set of basis vectors actually tells you the linear combination of basis vectors to use in order to describe this data in the amount of dimensions that are equal to the number of basis vectors. So that's how NMF does dimensionality reduction, where principal component analysis gives you transformed values, which are the projections of the data onto these principal components. NMF gives you these transformed values intrinsically in the H matrix, which is the which actually tells you literally the linear combinations of the basis vectors. So hopefully that was not too long of an explanation for you. Now let's actually see how NMF can be implemented. So to begin this, we frame it as an optimization problem. What is the distance between our approximate matrix V, or V hat, you could also say, that's W matrix multiplied with H. What's the distance of that to our original matrix V? And a distance measure that works really well for us is called the Kullback-Leibler, or KL divergence. And that's the formula for right there in the middle. And what you do is you minimize this Kullback-Leibler function in order to actually create a good approximation, right? And the way you minimize this is by using majorization, minimization, and applying Jensen's inequality. And if that doesn't make any sense to you, that's quite all right, and it shouldn't. If it does, then congratulations, that's quite impressive. You've got like a really good memory, or maybe you're in a math class right now. All we need to know is that this gives us the mathematical process that yields our algorithm. If you minimize this function, then you go ahead and get the NMF algorithm, which is exactly these 2 multiplicative update formulas. And so as you see here, if you put these multiplicative update formulas inside of a loop, then what you do is you first initialize two empty matrices, W and H, not empty, sorry, but with random values. And then what you do is you run this loop where you update H and W in succession using this input matrix V and themselves. And you keep updating until their product converges, or the product of W and H really doesn't get any more accurate of an approximation to the input matrix with each iteration. And this is usually just 100 or 200 iterations is basically the standard for this algorithm. And that's the implementation. Here you see it in code version. This is the class that we use in our notebook. The only difference between that and this is because for dimensionality reduction, the use of that, we want to specifically normalize our basis vectors after each update in order to ensure that they remain unit vectors. And just a quick validation of NMF, what we can do is do dimensionality reduction for visualization by reducing a toy data set that we can just make with pandas to reduce it down to 2 dimensions. And we can do this with our NMF and then scikit-learn's NMF library. And as you can see, here's around here, our transform values in this lower dimension look very similar. So our basis vectors are basically, we can conclude that our basis vectors are very similar, and, because we're projecting data that looks very similar. So there you have it. There's our NMF implementation. And then we also did some experimentation to compare it with PCA as done by Andrew and Griffin. So thanks for watching.
Okay. Gotcha. Kind of. All right. Let's bookmark this for later review in my bookmarking browser. Okay. And let's put this down. Okay, so why and how of non-negative matrix factorization. So non-negative matrix factorization has become a widely used tool for the analysis of high-dimensional data, as it automatically extracts sparse and meaningful features from a set of non-negative data vectors. We first illustrate this property of NMF on 3 applications: in image processing, text mining, and hyperspectral imaging. Then we address the problem of solving NMF, which is NP hard in general. They review the standard NMF algorithms and present recent subclasses of the problem. And then they describe the problem in math. So we know it's dimensional reduction. Got it. So NMF has become popular with its ability to automatically extract sparse, easy interpretable factors. And they're going to illustrate this in different applications. So let each column of the data matrix be a vectorized gray level image of a face. The entire vector, it generates 2 factors, W and H, so what we've been talking about, and it approximates using a linear combination of the columns, which they've talked about. Since W is non-negative, the columns of W can be interpreted as images with its vectors of pixel intensities, which we refer to as base images. As the weights in the linear combination are non-negative, these basis images can only be summed up to reconstruct each original image. Moreover, the larger number of images in the data set must be reconstructed approximately with only a few basis images. Hence, in the latter should be localized features found simultaneously in several. This is the initial facial image. These are the facial features that I found. Importance of features is H. And when you multiply, you get an approximation of J. Which, yeah, that's a pretty darn good approximation. It didn't find the eye colors and it made the mustache bigger. Text mining and text recovery. NMF identifies topics and simultaneously classifies the document among these different topics. So we have a document. It basically finds the importance of the documents after looking at the whole thing, just like it would. This is called bag of words model. Okay. And this was built off of this as a more complex implementation. Okay, that makes sense why I wouldn't know the original, because when I came into this. Okay. Hyperspectral unmixing. Okay, I think I'm good on the important things that I just desperately needed to know. Okay, so let's go to the next level of notebooks, because now we're looking at robust PCA that uses randomized SVD and uses LU factorization. Let's click it. Oh, cancel. I don't want to leave the page. I want a new tab. New tab. Okay. Here they build a background removal. And this used to be so state of the art, but now it's in like every single Photoshop competitor out there. And it used to be hard to do. And I was the guy who made a website. Well, I don't know if it's the only guy, but one of the guys who made a background removal website sold his stuff to Canva. It used to be a standalone website that he charged people for. Like if I could think of simple uses for AI and build a standalone website to do it, man, I just built a bunch of them and I wouldn't even have to work again. But I don't think about stuff like this. Like, would have never occurred to me that a background needed to be removed. Instead of just having something simple like that. Like, it has to be simple, it can't be complex. And I think in a lot of complex terms in my mind, which is unfortunate sometimes. Okay. So they have a human activity data set and a background subtraction website. Here, they're just importing the data and they have a video clip. And they're getting a sub-kip that they're just displaying here. And it plays. I'm betting part of this is like the foundation of some of those Gen AI video stuff of like how it integrates the background with the new pieces it's adding in. So it's going to create a data matrix because obviously computers cannot actually see anything in the video. It needs to be turned into numbers. And so it looks like it's doing that and creating clips and frames into, clipping it and creating like an image frame of it and then converting that into grayscale. You've seen this in the PyTorch stuff in week 1. Now they are looking to plot the images, which I might just need to learn this code. I've never worked in computer vision. I know a lot of juniors want to learn all the things, but you typically have a career specializing. And I specialize in predictive or prescriptive modeling, typically, or NLP. So I've worked in those are the only areas I've ever worked in. And I started out in a lot of NLP stuff, got into a lot of predictive stuff, and now they're merging together in a lot of ways. So I am doing that, but a lot of the deep learning applications use a lot of CV, computer vision, and this is a whole different world. But like they're talking about the topic modeling, some of the original versions of it, how to use it. I kind of need to know that for a lot of the NLP that's up on my plate these days. So we're going to get into it and see if this actually will produce better results than previous models. So this just enumerates the images to plot it, and then it makes a plot of the plot of images, adjust the scale and the resolution. Okay, so here we go. They're showing us the clip that they got and the grayscale it made, and the axis that we're working on and the size of like the image, so 200 by 300 image size. Then we're going to save it. That's great. Whoa, look at this. I have no idea what these squiggly lines are, but it's plotting something. Got it. Too big to plot. So what are the... I have no idea. They are saving it. So I guess I need to figure out what those wavy lines are. They might have told me and I missed it. Maybe they're unrolling the image instead of having a 2D picture. They have a big old column. Got it. So that's the unrolled image. That is not pretty at all. I mean, this just takes all the meaning out of the image. Anyone else think that? Well, I guess that's what computers need to understand it. So now they're going to attempt SVD. So they basically import in random decomposition of that original image, and we get this more smoothed out version of a decomposed image. The higher the resolution, the slower it is processed. So here it took out all of the identified dark blotted people and to process the people removal. And then this is the extracted people from that image that they had. You just kind of see the leftover residues. So rank 1 approximation. I might need to pull up the video and see what they mean by rank 1 approximation. So let me see. They've been pretty good at, well, I guess it doesn't matter if they're just using PCA anyway. But they've been pretty good at explaining it in the text, so I don't have to watch the video. You can watch the videos. There are videos. I can learn things through video. I don't really learn my math well by hearing people tell me the math equations, and I need to see it written out. Because it's like a language to me, but it's not a great spoken language, right? Data has low intrinsic dimensionality in order to alleviate the curse dimensionality scale. So you can basically do PCA with a truncated SVD. By creating a sum of two matrices, one that is a low rank and one that is sparse. And that's how they use background removal. Low rank can use a lot of redundant information, right? And sparse means mostly 0 entries. Yeah. Facial recognition, video surveillance, latent semantic indexes capturing common words used in all documents, while S captures the few keywords that best distinguish each document from others. Ranking and collaborative filtering a small portion of available rankings could be noise and tampered with. So outlier detection and big data. Actually, that would be a very interesting article to review. I am going to bookmark this. Okay. So L1 norm induces sparsity. Explains the stream on both corners. Maximum absolute column. The nuclear on which L1 is the normal singular value is trying to memorize the spark singular values are low rank. Actually, I want to see what they say. Okay. Whenever you're trying to understand a concept, oftentimes an intuitive answer is better than a mathematically rigorous one. This answer first highlights the difference between L1 and L2 loss and L1 and L2 regularization. Okay, loss versus regularization. Why is that what it is? Right. Sparse solutions 3 and 4 are pictorially defined in the following diagram. Feasible set because of that. The minimum is always attained at one of the corners in L1. The corner is described as having a non-zero coordinate with remaining coordinates being zero. On the other hand, L2 is a normal ball and does not have sharp intersection with the function. Although the tangent point may be observed, actually a whole bunch of neighboring points also contact that function line. This is why L2 is not sparse. Got it, because it's tangent. The advantage of the loss function is less known, and that's why I'm going to put a time here. It is robust to outliers. Pictorially define a set of numbers in position. Never mind. Right. Switch term blows the error differences. Okay. And minimize the algorithm Russian to fix the solution. Inadvertently focused on the majority on the outliers and less on the actual data. Does not place emphasis on the outliers. It's robust to them. This is because they're inherently defined. Okay. Got it. Things that you just miss in concept when you aren't in the research side of the business. I typically just know when to use them, not the why of or what else might be. Different ends of the house. Okay. So let's go back. So now we're looking at our optimization, right? That's what we were talking about. So, and they're implemented from the paper. Yeah, if you want to be a research data scientist, knowing that math from that paper, paramount. And it is not easy. Because I've been going back through data structures and algorithms in my brain. It's just like, why are you doing it that way? It is so wrong. But I know there's a way to do this. Right, you don't need to know any of that. You just need to take this and write it into code. So we went from pseudocode to, that's still pseudocode. Okay, now we're into the real code. How do you do each portion of it? And they've named it by what it means. So not converged, while loop. So they do all of the components inside of the algorithm loop and all of the components inside of the algorithm. And then they do a loop here, I think. No. Yeah, they do a loop there. And this is LK1, LK plus 1. So much stuff. LK plus 1 equals D mu. Just have to be able to interpret the math. And actually, I think I want a whole section on just, I need to like put that next to each other. Let's do it now. What's the point? We're here to look at vector math in Python, so let's just do it. To it. Okay. Here we go. And now because I'm blind as a bat. Okay. So converged. We have an algorithm log norm. So we're just going to leave that here for now. It's actually the value of m. So we have m minus tau. Return sine m where s is greater than 0. That's just the interval here. Then we have the rank. SVD is just SVD on this. Oh, goodness. This is L. This is X. This is definitely hard to understand. I might need a whole section just to get through the math. A whole, like, a week. Because it's not that I don't understand the code. It's not that I don't necessarily understand the math. Actually, maybe I don't understand the math. Because if I understand the code and I'm not able to connect them, what does that mean? So actually, I think I might need to like write out the math in like smaller components of what's behind this. Because this is tau or mu. Yeah, this is mu. And this is mu inverse times yk, which makes me think this was z. What's z? So we have, it gets mu, which is mu. Yeah, they wanted a whole lesson on that. It's not happening this week. But I'm also not a research data scientist, so I typically don't have to implement. But a lot of the jobs I think I want in the future, either I'm going to have to direct teams or I'm going to have to implement better. Because it's like two different levels of working in this field. I do more business data science, so I'm not really developing the stuff, I'm implementing it across an organization. Whereas you have the people who develop the stuff and you typically get to work at more of the tech companies whose bread and butter are developing stuff to outpace their competitors. Okay, so LU factorization, a randomized range finder that uses LU factorization, which factors a matrix into the product from a lower triangular matrix and an upper triangular matrix. Yeah, I'm going to forget. how they got it. So yeah, let's go to the Khan Academy video. I mean, linear algebra was a good decade ago for me, so probably exactly a decade. So now it's 2024, so it's over a decade for me.
Figure it never hurts getting as much practice as possible solving systems of linear equations. So let's solve this. What I'm going to do is I'm going to solve it using an augmented matrix, and I'm going to put it in reduced row echelon form. So what's the augmented matrix for this system of equations? 3 unknowns with 3 equations. So it'll be, I'll just have to do the coefficients. So the coefficients of the x terms are just 1, 1, 1. Coefficients of the y terms are 1, 2, and 3. Coefficients of the z terms are 1, 3, and 4. 1, 3, and 4. And let me show that's augmented. And then they equal 3, 0, 3, 0, and minus 2. Now I want to get this augmented matrix into reduced row echelon form. So the first thing, I have a 1 leading 1 here. That's a pivot entry. Let me make everything else in that column equal to a 0. So I'm not going to change my first row. So it'll just be a 1, a 1, a 1, my dividing line, and then I have a 3. Now to zero this out, let me just replace the second row with the first row minus the second row. So 1 minus 1 is 0. 1 minus 2 is 1 minus 2. Actually, a better thing to do, because I eventually want this to be 1 anyway. Let me replace this row with the second row minus the first row instead of the first row minus the second row. I can do it either way. So the second row minus the first row. So 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. And then 0 minus 3 is minus 3. Now, I want to also zero this out. So let me replace this guy with this equation minus that equation. So 1 minus 1 is 0. 3 minus 1 is 2. 4 minus 1 is 3. Minus 2 minus 3 is minus 5. Fair enough. So I got my pivot entry here. I have another pivot entry here. It's to the right of this one, which is what I want for reduced row echelon form. Now I need to target this entry and that entry. I need to zero them out. So let's do it. So I'm going to keep my second row the same. My second row is 0, 1, 2, and then I have a minus 3, the augmented part of it. And to zero this guy out, what I can do is I can replace the first row with the first row minus the second row. So I get 1 minus 0 is 1. 1 minus 1, there's a bird outside. Let me close my window. So where was I? I'm replacing the first row with the first row minus the second row. So 1 minus 0 is 1. 1 minus 1 is 0. I don't want to make it. 1 minus 1 is 0. 1 minus 2 is minus 1. And then 3 minus 3. So that's equal to 3 plus 3. So that's equal to 6, right? 1 minus 0 is 1. 1 minus 1 is 0, negative 1. And then 3 minus negative 3, that's 6. I always want to make sure I don't make a careless mistake. Now let me get rid of this entry right here. Let me zero that out. So let me replace the third row with the third row minus 2 times the second row. So we have 0 minus 2 times 0. That's just going to be 0. 2 minus 2 times 1. That's 2 minus 2. That's 0. 3 minus 2 times 2. That's 3 minus 4, or minus 1. And then finally, minus 5 minus 2 times minus 3. Let me write that down. Minus 5 minus 2 times minus 3. It's minus 5 minus 6. That's minus 5 plus 6 is equal to 1. I really wanted to make sure I didn't make a careless mistake there. So that is equal to 1. So I'm almost done, but I'm still not in reduced row echelon form. This has to be a positive 1 in order to get there. It can't be anything other than a 1. That's just a style of reduced row echelon form. And then these guys up here have to be zeroed out. Well, the easy thing to do, let me just multiply this equation by minus 1. So then this becomes a plus 1, and then that becomes a minus 1. And then I just need to zero out these two guys up here. So let's do it. So my equation, I'm going to keep my third row the same. My third row is now 0, 0, 1, minus 1. 0, 0, 1, minus 1. And now I want to zero this guy out. So what I can do is I can set my first row equal to my first row plus my last row, because if these two add up, they're going to be equal to 0. So what do I get? 1 plus 0 is 1. 0 plus 0 is 0. Minus 1 plus 1 is 0. 6 plus minus 1 is 5. Now I want to zero this row out. And to zero this row out, what I can do is I'll replace it with the second row minus 2 times the first row. Right? So 0 minus 2 times 0 is just 0. 1 minus 2 times 0 is just 1. 2 minus 2 times 1 is 0. Minus 3 minus 2 times negative 1. Let me write that down. Minus 3 minus 2 times minus 1. Don't want to make a careless mistake. So what is that equal to? This is equal to minus 3 minus 2, or minus 3 plus 2, which is equal to minus 1. So that's equal to minus 1. And now I have my augmented matrix in reduced row echelon form. Reduced row echelon form. My pivot entries are the only entries in their columns. They're each pivot entry in each successive row is to the right of the pivot entry before it, and actually have no free variables. Every column has a pivot entry. So let's go back from the augmented matrix world and kind of put back our variables there. So what do we get? We get x plus 0y plus 0z is equal to 5. That's that row right there. We get 0x plus 1y plus 1y plus 0z is equal to minus 1. That's that row right there. And then finally, we have 0x plus 0y plus 1z is equal to minus 1. That's that row right there. And just like that, we've actually solved our system of 3 equations with 3 unknowns. That's the solution right there. I just wrote it in this way just so you see it corresponding, but obviously I could have written them closer to their equal sign. So hopefully you found that vaguely useful.
Okay. Yes, I did find it vaguely useful. So that explains that Gaussian elimination. Actually, used to love doing this in college after that refresher, I know what he's talking about. So let's look at this is how you would compute it. Lower unit triangular, all diagonal entries are 1. And that would be NPI and NP copy. That is how we would compute it. Okay. Okay. Okay, I'm not going to do the exercises right now. I just want to get through it. I'll probably come back tomorrow and do that. Yeah, the right answer to the right question. Yeah, I need to do the homework for sure. But I'm going to read through it and go back. This whole section seems to be making sure you understand how it works. My brain, it burns. If I see Gaussian again, oh man. Someone must feel my pain. Like reviewing stuff that I guess I should have kept up with it sooner. That is more on the statistical side. Okay. Wow, 200 BC in Chinese. I have to read this book. I wonder if there's a translation. Fascinating. Can you imagine having this knowledge back then? Like, I wouldn't have never thought that this was a thing back then. 200 BC. That is so cool. Imagine, like, we assume they were so not up to date on stuff, but they're still teaching us things. Wonder how all the ways they wrote down that they used were like, what are the ways we don't know that was destroyed? That's kind of cool. Well, paralyzation, clearly, yeah. Okay, so what I think tomorrow is I'm going to come back and try to do some of the coding. I just hate coding after like 12 and like before 8, but I'm sleeping at 8, so I either need to be up at midnight or really early in the morning. My coding brain to be on, but we're going to try to make it happen. Use afternoons to plan, to study, to organize, to communicate with people. Just how my brain works. Some days is unfortunate, like today. All right, so thanks for holding me accountable to showing up. You're welcome to keep along the track I'm doing or to go your own track as you study the materials. DM me and let me know what you're studying if I don't already know you. And y'all have a great rest of your day.